Alright, so today we're going to continue on in 7.2. Alright, last time I introduced first order partial derivatives, and we practiced a few. And so this second part of that is just looking at more first order derivatives. These are going to be a little more complex. They're going to involve our chain rule, our product rule, and going to be a little more involved. And so we'll look at some additional multivariable functions and their first order derivatives. Alright, so the first function we're going to look at today is this f of xy, where I've got x times y squared times e to the 2x. Alright, I'm going to find the first order derivative with respect to x. So again, remember what that means. I'm going to find the change in my function with respect to x. So first order derivative with respect to x. Alright, now x, if you look at the function, there are two x values. There's this x in front that's multiplying out here in the front times 2 times y squared times the second e term, which also has x value in it. And they're being multiplied. And so I actually have x times y squared times e to the 2x. And so this is going to require my product rule. And then on the e to the 2x, I have the chain on the e term. Alright, now I'm going to pair the y squared with the x, since x is the simpler function. Right, remember y squared behaves like a number. It would be like if it was x times 10, right? And then the e to the 2x is going to be my second function. So my first function is x times y squared. The second function is e to the 2x, which that one's going to require my chain rule. Alright, so product rule first, derivative of the second, plus second, derivative of the first. Alright, so the first function is x to the y squared, since I'm pairing the y squared with x. Then the derivative of the second, derivative of the e term, is where I'm going to have to use my chain. It's e to the 2x. Don't forget then times also a 2, right? That's the chain rule. Derivative of the outside is the e part, times the derivative of the inside is where the 2 comes from. Plus the second, e to the 2x, times the derivative of the first. So I'm looking at my first function, which is x times y squared. Remember, y squared behaves like a constant, therefore we treat it like a constant. It would be as if it was like 10 times x, right? If it was 10 times x, the derivative would be 10. Well, it's y squared times x, so the derivative is y squared, because y squared behaves and therefore is treated like a constant. The derivative of x is just 1. Alright, and so there's my derivative with respect to x. I will clean it up a little bit, right? I can simplify this by factoring, and so I will do that. Just a good rule of thumb to practice simplifying by factoring. Alright, both terms have our x squared, I could pull that out, and both terms have an e to the 2x, so I can pull that out. So I'm going to factor out a y squared, I'm going to factor out an e to the 2x. What's left over when I factor those out? Remember, I'm dividing them out. And so in the first term, I still have a 2 and an x, so a 2x. In the second term, I divided everything out. And so when I divide everything out, remember there's still a 1 left over. Alright, so there is my first order derivative of this function with respect to x. Alright, now with respect to y. So I'm going to go back and look at my function and take its derivative with respect to y. Alright, the change in my function over the change in y. So y is the variable that's changing. X is being held constant. Alright, well there's only one y term, right? The y squared. The x parts are just constants. They're unknown constants, but they're fixed, so they're constant. They're considered constant, they behave like a constant, they're treated like a constant. And so x is multiplying and the e to the 2x is multiplying, and so they're constant multipliers, and so they just come along. X times e to the 2x are constants. Alright, the part I'm taking the derivative of is the y squared. So it's the constant times the derivative of the y squared. Well, the derivative of y squared is 2y. Alright, which again, if you left it like that, that's fine. I will rewrite it. It's just, rule of thumb is to move the 2y to the front and actually write it in the right order. So 2x, y, e to the 2x. But again, like I said, that's minor. Either one of those would be acceptable. And there's my first order derivative with respect to y. So y is much easier. I didn't have to use any special rules with y. It was just the derivative of y squared. All I had to remember is that x behaved like a constant. E to the 2x also behaved like a constant. And so they're just constant multipliers that come along. Alright, the next one. Alright, and this one again is just the way this works. This is raised to the 3 halves, so that is a power outside. So it's this group inside, raised to the power 3 halves. Alright, so I have to use my chain rule with the power outside, and that's the only rule besides my, making sure I pay attention to which variable I'm taking the derivative of. Alright, so chain rule. Alright, so the change in my function with respect to the change in x, so the derivative of my function with respect to x. Alright, so it's the chain rule. The outside part is the power 3 halves. So remember, the chain rule is I take care of the outside, leave the inside, and then separated by multiplication, we take the derivative of the inside. Alright, so the outside is just the power. And so the power, I pull the power out front. Right, the 3 halves comes out front. And then I leave the group inside exactly the same. I don't do anything to it. But I take my power raised to 1 degree less. I take my 3 halves, subtract 1, and so I'm going to be left with a positive 1/2 out front. Alright, there's the outside. Separate, I take the derivative of the inside. So when I take the derivative of the inside, I got to pay attention to which variable I'm taking the derivative of. So it's the x part. Alright, so the x parts is what I'm taking the derivative of. Everything else is behaving like a constant. The 3 is a constant. Y is behaving like a constant. Well, they're constant multipliers. They come along. I'm taking the derivative of the x squared part. Well, the derivative of x squared is 2x. Alright, so there's the derivative of the first term. Alright, the second term is 5x. Well, the derivative of 5x with respect to x is 5. Right, and then you can clean that up a little bit. So the first part stays the same. And then I could take the 2x times 3 to get 6xy plus 5. And there is my first order derivative with respect to x. Alright, now the derivative with respect to y. Alright, so the change in my function with respect to the change in y, so f sub y. Still the, again, power rule outside. And what's interesting about this, or what you should notice about this, is the power rule outside doesn't care if I'm taking the derivative with respect to x or y. It behaves the same way because, again, it's not affected by either variable. And so the very first part of this is exactly the same as the x variable. Right? The very first part is I do my power rule. 3 halves, leave the stuff inside the same. Raised to the subtract 1, raised to the positive 1/2, alright, which is exactly the same as our previous derivative. What matters is when I take the derivative of the inside, and that's when it matters which variable I'm looking at. So remember, times the derivative of the inside, well, now I'm looking at the change in y. There's only one y part on the inside, and so that's the part I'm taking the derivative of. The 3 is a constant, the x squared's behaving like a constant, so they behave the same way. They're constant multipliers, they come along. And I'm taking the derivative of the y part. Well, the derivative of y is just 1. And I'm going to write it down, although, again, usually we don't. But I'm writing it down to indicate to you that's what it is. I'm taking the derivative of y, which is 1. The 3 and the x squared constant multipliers that come along. The 5x will zero out, right? Because there's no y term. There's no change in y, and it zeroes away. All right, so there's the derivative with respect to y. All right, next example. Alright, so I've got my e to the x squared plus y squared minus 6. So I've got my e term raised to a function of x and y. And so again, it's my e term and the chain rule with my multivariable functions. And so it's going to be the change in my g over the change in x first, so g sub x. Alright, so I'm taking my derivative with respect to x. So again, chain rule. Derivative of the exponential is the outside. The x squared, y squared minus 6 is the inside. And so remember, the derivative of the exponential is the exponential. And so the first thing you do is you write down the e term exactly as is without changing one thing about it. And then separately, separated by multiplication, we take the derivative of the inside. It's the inside where it matters which variable I'm looking at. The outside doesn't, right? So the outside is the same whether I'm taking the derivative with respect to x or y. Alright, so the derivative of the inside with respect to x, well, there's just the 1x term, the x squared. The rest of it will zero out because there's no x terms in the rest of it. And so it's just the derivative of x squared, which is 2x. Alright, done. There we go. There's really not much to clean up there, so I'm just going to leave it. Now I'm going to take my first derivative with respect to y. So the change in my g with respect to y, so g sub y. First part's the same. Derivative of the e is the e, and so I rewrite my original expression as is. Alright, then it's times the derivative of the inside, and this is where it matters that I'm looking at the y parts. Alright, there are my y parts. The x squared zeroes out, so it's just the derivative of y squared, which is 2y, and a negative minus 6. Alright, derivative of negative 6y is negative 6, and there's the derivative of that term with respect to y. Alright, the next example. Alright, so this one's just a little more complex because there's just a lot going on in it. Alright, so there's a lot of terms with mixed values that I got to keep track of when I take my derivatives. Alright, so my derivative with respect to x, so my change in my function with respect to the change in x, f sub x. Right, every single term has an x term. Right, all of them have an x term in it, and so I'll be taking the derivative of every single one of them when I take the derivative with respect to x. This one will require the chain rule, right? E to the 2x requires my chain rule because there's a 2 inside with the x. Alright, 4x cubed, well that's just power rule, 12x to the second, minus the 5 is a constant multiplier, it comes along. The y squared behaves just like the 5. It's a constant multiplier. It comes along. I'm taking the derivative of just x. Well, the derivative of just x is 1. And this time I'm going to leave it off. It'd be times 1. Alright, so again, I'm going to leave just the 5y squared. Oops. The next term, again, the y to the 4th is just a constant that's going to come along. Right, it would be as if it was 10 times x cubed. Alright, so the y to the 4th is a constant multiplier that comes along. I take the derivative of the x cubed. So it's up to you. You can write down the y to the 4th right away so you don't forget. And then take it times the derivative of the x part, which would be 3x squared. Or you can write it the other way around. Either way is fine. Alright, then the last term, e to the 2x, which again is just the derivative of e using the chain rule. So e to the 2x times 2. And if you want to rewrite it, you can. I'm not. There's not a whole lot to do to rewrite it. Nothing really collects. There's no like terms, nothing factors. And so I'm just going to leave it like this. And so there's the derivative of that function with respect to x. Right now with respect to y. Alright, so you'll notice there's less y terms. Alright, there's no y term there. There is one here. And there is one there. And there's no y term at the end. So it means those will zero out, right? There's no change in y, therefore when I take the derivative with respect to the change in y, they zero away. And so it's just the two middle terms I'm taking the derivative of. Alright, so in the first term here, the 5 is a constant, the x is a constant, they come along, it's a negative 5, don't forget the negative. So negative 5x comes along, it's the derivative of the y part I'm taking, so the derivative of y squared is 2y. Alright, the second one, the x cubed is a constant, so it comes along. It's the derivative of the y part I'm taking, so the derivative of y to the 4th is 4y cubed. And again, not a huge deal, but I will clean this one up a little bit. I'm going to take the 2 times the negative 5 to get negative 10xy, and I'm going to move the 4 to the front, just because, again, it's just a little more proper to write it that way. Right? And there's the derivative of that function with respect to y. Alright, the last one. Alright, so we've got a logarithm rule. Alright, so we've got the natural log of x squared plus y squared. Alright, so I've got my log rule and the chain rule. So this is my natural log and my chain. Alright, because again, something other than just a single variable inside. Alright, there's obviously a function inside of x and y. Alright, so take the derivative with respect to x first. So f sub x. Alright, remember the natural log rule is 1 over the function inside times the derivative of the function inside, and this time I have to pay attention which variable I'm taking the derivative of. Alright, so first step is 1 over what's inside. So 1 over x squared plus y squared. But I'm not done, right? Chain rules, I take the derivative of the inside. This is where it matters which variable I'm looking at. I take the derivative of the inside with respect to x. Well, I'm taking the derivative of x squared. So I get a times 2x. Y squared zeroes out. What you do usually write this as a single fraction. So it would be 2x over x squared plus y squared. And there would be my derivative with respect to x. The derivative with respect to y is going to be very, very similar. There's only one difference in the derivative with respect to y. Alright, so the derivative with respect to y next, f sub y. So the first part's the same. The derivative of the natural log, the beginning of it, doesn't care whether it's an x variable or y variable. It's 1 over what's inside. Then when I take the derivative of what's inside, it matters which variable I'm looking at. Alright, so the first part's the same. 1 over x squared plus y squared. But then it's times the derivative of the inside. Now it matters that I'm looking at my y variable. So I take the derivative of y squared, which is going to give me a 2y. Alright, so again, that's the only difference. I get 2y up top divided by the x squared plus y. But it is different, right? If I plug the number into that, I'd get a different answer depending on what my x value and my y values were. Alright, so there's my first derivatives with respect to x and with respect to y. Alright, so that wraps that up. The next set of notes that we're going to be looking at are going to be second order derivatives. Alright, we're going to be finding second derivatives. Alright, and that's the next set of notes. Alright, so we'll wrap that up there. So make sure you practice these. Go and practice on Connect and in the practice worksheets I've posted on ReggieNet.